Welcome to geometry class. Today we're going to talk about medians in triangles. Medians are particular segments that we can identify in triangles. And we identify those in ways similar to some of the lines and segments we've already been identifying. A median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. Let's just take a quick look at what that means. So given a triangle, any triangle, if I ask you to identify a median, first of all, be aware there are three medians in every triangle. Let's just look at the median that has endpoint at point A, or at vertex A. So in order to identify that median, we first have to find the midpoint of the opposite side. So I know one of the endpoints will be at A, and the other midpoint will be somewhere across on segment BC. So we need to find that midpoint. Once we know where the midpoint of BC is, we can connect A to that midpoint with a straight segment, and that is called a median. Sometimes people get medians confused with midsegments. Remember, a midsegment joins two midpoints of two sides. A median, which is what we're talking about now, joins a vertex to the midpoint of the opposite side. I'll go ahead and sketch in the medians of the other two vertices real quick, just so you can get a picture of where they are. So the median from vertex B goes across the triangle to the midpoint of AC, and the median of vertex C goes across the triangle to the opposite side to the midpoint of AB. You can see those are the three medians in triangle ABC. You'll notice if you look, of course this is just a rough sketch, but you'll notice there's this interesting little triangle developing in here. That actually should be a single point. Remember, we're in the context of these points of concurrency we're talking about. In fact, if we carefully construct the three medians of a triangle, we will find that they are concurrent at a point. That brings us to the Centroid Theorem. The Centroid Theorem says that the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. That point is called the centroid. So when we construct the three medians in a triangle, those three medians all intersect at a single point. That single point is called the centroid. Let's take a look at the construction now.
The construction of the centroid always begins with finding the midpoints of the sides of the triangle. And that's because the centroid is the point of concurrency of the three medians, and a median is a segment that goes from a vertex of a triangle to the midpoint of the opposite side. So the first thing we need to do is make sure we know how to find the midpoint of a line segment. The way that we find the midpoint of a line segment is we basically start with the perpendicular bisector construction. So if I want to find the midpoint of this segment here, I begin as though I were trying to find the perpendicular bisector. So I'll make an arc above and below, come to the opposite side, that is the opposite endpoint, cross above and below. And now we know that if I put my ruler here, my straight edge that is, between these 2 points lies the perpendicular bisector. But I'm not interested in the perpendicular bisector. All I want is the midpoint. So I'll just mark it here. And that is the midpoint of my line segment. In other words, we can be sure that if this is A and B, this is M, and these are congruent and those are congruent. So that's what we'll do to find the midpoint in our triangle when we try to construct the centroid. We'll start here with just a random triangle, as I normally do. We'll use this one. And we want to construct a centroid. Again, the centroid is the point of concurrency of the three medians. So we'll go ahead and start with finding the midpoints of each of these three sides. I'll start with side AB. Again, here's our perpendicular bisector. We're interested only in the midpoint, right there. Now we'll go to BC. And mark our midpoint there. and then we'll go to AC. And there we have our three midpoints. Once we've identified the three midpoints, the construction actually becomes quite simple. All I need to do is connect vertex A to the midpoint of the opposite side CB, like that. That's one median. Then connect vertex B to the opposite side at the midpoint. There's my second median. And connect point C to the midpoint of the opposite side. There's my third median. And there is my point of concurrency. In this case, it is called the centroid. The construction, the mechanics of the construction, are largely the same as the mechanics of the construction of the perpendicular bisectors. However, instead of drawing in the perpendicular bisectors, we just mark the midpoints and then connect it to the opposite vertex. Keep in mind again that the centroid is always located 2/3 the distance from the vertex to the midpoint of the opposite side. In other words, if I were to come into this diagram and begin to label some of these values with variables, for instance, we call this segment here, we say that it's x units long. That means this segment here would be 2x. If this segment here were y units long, then this segment would be 2y. And if this segment here were z units long, then this segment over here would be 2z units long. That also helps us to find distances. So for instance, if this were point D over here, and we knew that dB is 9 units, then we could be sure that this y is equal to 3, and this 2y actually equals 6. So keep that in mind, that the centroid is always located 2/3 the distance from the vertex to the opposite side. It's also the balance point of the triangle. We'll take a look at that in just a moment.
All right, we've seen the construction. Remember that when we talk about the centroid, if I were to, again, just sketch in a centroid here. And to do that, I'll just draw in two of the medians, because remember, if we identify two of the medians, that will be enough for us to determine where the point of concurrency is. So here's my centroid right here. The theorem says that these medians are concurrent at a point called the centroid, and that that point is located along the median 2/3 the distance from the vertex. So if I look at this in here and call this A, then this must be 1/2 A. And so we see there's this fixed mathematical relationship. It's one of the things you need to know and remember about a centroid. You may get a problem where, for instance, you may have something that looks like this, and there'll be a single median drawn in here. Suppose we know that these are congruent. And perhaps we'll have a point here identified, call that point A. And suppose we're also told that A is the centroid. A is the centroid. And then we're asked, what is the length of segment AB if segment AC, the length of segment AC is equal to 12? What does that mean with respect to segment AB? Well, we know that AB is 1/3 of BC. That is 1/3 the distance across that entire median. And so therefore, since AC is 2/3 of the median and AB is 1/3 the median, that means that AC must be twice as long as AB. Therefore, AB equals 6. So we can find that fixed mathematical relationship. We can actually use that to find some values in the triangle. One other thing we need to know about centroid, and that is that the centroid is also called the center of gravity. All that means is that if we had a physical triangle or a amount of material that was formed into a triangle, the centroid would actually be the balance point. And we can actually take a look at this. Here is just an ordinary piece of wood. You can see it's triangular in shape. You can also see perhaps I've labeled 2 points on here. I've constructed just 2 points on here. This one is the in-center and this one is the centroid. And so I just like to demonstrate that if I use the tip of my pencil, I can actually get this piece of wood to balance on the centroid. Just give it a little bit of a spin to get a little stability, but you watch as it comes to rest, it just rests right on the centroid. Now, you may look at that and say, well, Mr. Picard, there's a hole in there. That's why it stays there. Well, let's just try it on the inside. There's a little hole there too, just a little impression. Can we get it to sort of stay on the inside? Let's just give it a shot. Try it again. Right, you can see pretty clearly that it just will not. And in fact, if I sort of ease it on there, you can see a little bit more clearly that there's clearly a weight on this side, on the long side here. And that's because I'm not on the inside. If I move it toward the centroid, then it will tend to balance a lot better. You can see that it's sort of balanced out. And to just demonstrate that with the finger, you can see if I put it on the centroid, again, I'm not sure if you can read that, but if I put it on my finger at the centroid, I can actually get that triangle to balance on my finger. Okay, so the centroid is the balance point. That's the point at which the triangle will balance, because assuming the material is distributed evenly across the triangle, that's just where it all balances out. That's why it's called the centroid. So, a couple things you need to remember about the centroid theorem and centroids generally. Number one, the centroid is the point of concurrency of the three medians. The medians are segments that have as their endpoints a vertex in the midpoint of the opposite side. And then you should also know that the centroid is called the center of gravity, or the balance point of the triangle. As always, work through a few practice problems. Try the construction of the centroid a few times on your own. If you have any questions, shoot me an email.